Hey everybody, this is Larry. This is day 28th of the April Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Today is the 28th, the last day of week 4, and we're almost done with April. Hope y'all are enjoying so far, and today's problem is Unique Paths 2. So with this problem, I usually start with live, so if it's a little bit slow, just fast forward or whatever you need to do. Always need that disclaimer because people keep on telling me that I don't explain the problem well enough. I'm like, yeah, that's not the point. But okay, so to this problem, you start with the top left, you want to move down or right, and now the obstacles. How many unique paths there are? So if there's no obstacles, you could actually look up binomial formula, and it's actually kind of an interesting proof if you want to play around with that. But this one is actually, I don't know what unique path 1 is. But this is a relatively straightforward dynamic programming problem. The first thing to notice is that, the first thing I noticed, to be honest, is that I've done this problem or a similar grid E problems many a times. So to me, I just knew it was going to be dynamic programming, unless the dimensions are too big that we have to figure out a different strategy. And given that m and n is less than 100, that should be fast enough because this dynamic programming should be linear in the size of the input. But maybe we're jumping ahead a little bit. The other thing to notice is that, so what separates this problem with another grid problem, right? Well, in this case, this graph or this implicit graph, or, with respect to let's say you draw an edge, a directed edge from where a robot is, or each cell that a robot can be, and the next location that the robot can be at. Well, in that case, if you look at that graph, it is a DAG, right? And it's directly directed and it's asynchronous, right? So there's no cycles, and because there's no cycles, dynamic programming is a very good it's a good question to ask whether that could be true. And in this case, so there are a couple of variations to this problem. There's the minimization or maximization or something like that, depending on what you do, like picking up apples or something. I don't know. But just based on that, that just changes the function. But the transition is roughly mostly the same. The only thing that you have to consider is that there are obstacles, and you shouldn't be an obstacle. Or you shouldn't be in a path that has an obstacle in it. Okay. And to be honest, this kind of problem, I usually go bottoms up, and there's a very, it's a good transition, but I recommend just doing it both top down and bottoms up, and then, the one with the space compression or the space optimization, as I would call it, to get it down to all of maybe m or n space or something like that. And with that, I have a link. I have like a walkthrough of how to do that. So I have a link below. But cool. Let's get started. I'm gonna do just the top-down version, and then we'll see where it goes. Depending on how tired I am. But let's say count from any x and y, right? So that said, rows is equal to length of obstacle grid. I'm going to rename this to something shorter to type. Though, for interview purposes or whatever, maybe I would not. I might, long and descriptive is okay, but make sure that this is at least 1 so I don't have to check. Okay. So, for an actual interview, I recommend just keeping it long because descriptive names are better, but for now I'm just going to do this. So let's see. So if m of x, y, well, we have to keep track of the bounds first. I'm just trying to see if 1 is so 1 is, there's an obstacle, so we have to return 0 here because there's no path that goes through if there's an obstacle. So we're just going for the base case. If what is the other one? There are a couple of ways to do it as well, or depending on how you want to define certain things. But I'm gonna play around, and this is probably not the way that I usually do it. But if x is greater than or equal to rows, or y is greater than or equal to columns, we return 0 for the same reason that they're just out of bounds, so there's no paths. And then if these constraints are good, then if x is equal to rows minus 1 and y is equal to columns minus 1, we return 1 because if you're already at the end point. So let's step back a second. So what is this function, right? Count the number of ways to reach the lower right corner from xy, right? So if we're already there, then that's by default one way of getting there from from itself, almost like a mathematical identity thing. So then now we can think about the transition, right? Well, raise is equal to 0. And I would also say that this is awkward though, because this can overflow. So you just have to trust that. Because I'm looking at the constraints here, because I'm not like, okay, the math can overflow. That was like, maybe I forgot something and that it cannot overflow. But no, I'm pretty sure this can overflow. So I think maybe for this problem, maybe it's an older problem or something like that, where you just have to trust that it won't overflow. And in Python, I wouldn't worry that much about it anyway for that reason. But it is a little bit awkward. So if you're in Java or C++, you'll be like, okay. Because what I was going to say is, if m and n is less than 30, say, or something like that, 30 or 25 or whatever, because of the binomial formula, you can kind of work it out so that like maybe the constraints are such in a way that it doesn't overflow. That's not the case here though. So yeah. Anyway, so that's what I was thinking about when I get here. And then now we have two paths, right? One is go right. So how many ways are there if we went right? If we went right, then we just recursively say, okay, we went right. So the number of ways to reach the lower right corner is at our current spot, going right or going down, right? So that they both create a distinct way from this branching point. And then at the end, we just return ways. And then we can just return count from 0, 0, and we're let's just say mostly done, not actually done, because again, this is going to take a long time, just on the fact that let's see where oh, okay, so this is the other one. There are only 2 test cases. Okay, fine. Yeah, so this looks good, but it is going to be too slow, and we can kind of show that in a bit. I'm just gonna, was it 100? I don't know what this is, but this looks like it's good now because I didn't count. And this should time out because, okay, maybe not. Wow, did I not do that much? Do that many? I thought this looked like a lot, but Did I cache by accident? Huh. That's remarkably fast. Oh, I guess it's only 107 paths. What I need to do is actually this, but with 0, so then there are more paths. I mean, I was just lazy, so I was just copy and pasting. And this, in theory, should time out. Maybe not. Who knows anymore? Wow. Yeah, I'm really bad at this, clearly. But my point is that it should time out with big enough. If this is 100 by 100, it should definitely time out. I was just a little bit lazy about the counting. Okay, well, mistakes were made, but unless I cached by accident, nope. Okay, well, my bad attempt to show you that it'll time out aside, this should time out for 100 times 100 because there's just way too many paths. Maybe now I'm annoyed that I didn't show it, so I'm gonna show it. So let's actually count. That's 10. So that's 100. Okay, this is 50 by 100. I think that should be big enough. Unless I miscounted, then I would just be sad. Okay, so now you can see that it is timing out as predicted. But yeah. So what are you going to do, right? Well, and if you are familiar with dynamic programming, you're probably already ahead of what I'm going to say and know that what I'm going to say, which is that this function, for every input, we know that it's going to be give us the same output, right? And so we do something called memorization, which is just that we memorize that this is a function, meaning that for every same input we get the same output. So why not just save it somewhere next time, right? So let's do that paradigm. I usually write it out so that it's easier to see and explain. But yeah, let's say has cache is equal to this times oops. On my laptop keyboard today, so I'm a little bit awkward. But yeah, so now we have this cache, and then now we can just check it a little bit. Yeah, we'll check it after the bounds. It doesn't really matter as long as because they're both lookups. But if has cache of xy, then we return cache of xy, and then at the very end we just save it down. Oops. I know that it's obviously easier if you're familiar with I don't know, LRU cache or whatever in general. It is. Ooh, this is well. I mean, we knew that it was just going to be big. Though, I mean, is there a mod that I forgot? Maybe I forgot a mod. It just may be that this is not a valid input in data, or that's not in their input. I mean, it is definitely a valid input, right? But in any case, yeah, I mean, that seems right. Yeah, as you can see, I know that people talk about like, hey, is it okay to ask, use LRU cache or something like that in interviews? But you can see that like I did this in 6 lines of code, I guess, and I did it in about 30 seconds, right? So, do you need it? I mean, I do it on contest or interview, or yeah, I do it in contest because I want to focus on other stuff, and sometimes you do make typos and stuff like that. But in the contest, you're not trying to explain to someone how your code works necessarily. So yeah, so I would definitely recommend just doing this, because then now you can explain the complexity also in an easier way. So this is going to be straightforward. We just count the number of inputs, right? The number of possible inputs. X could be from 0 to 2 rows. Y it could be from 0 to columns. So the total number of possible inputs is O of rows times columns. Fair enough, right? Because this is their row numbers here, their columns numbers here, so it's gonna be row times columns. Let's see, what's the other thing? So that's time. Oh, sorry. So that's the number of possible input. So that's also going to be space complexity, because for each one you're storing O of one object, which is just the hash cache object, and also just the cache raised object. And then the other thing is what's the time complexity, right? Well, if you look at this function, everything will have an O of 1, because we can assume that at this point this is O of 1. Everything has an O of 1 complexity. So then your total time complexity is just the number of possible inputs times the amount of time you spend on each core. So it's going to be also O of R times columns for time complexity. Okay. So what does this mean, right? This means that this is linear in the size of the input, because the input is rows times columns, as we know. So yeah, linear in time and space. That's all I have for this problem. For an additional, like, making sure you understand this, try to do it bottoms up as well. I find that this problem is relatively straightforward to do bottoms up, and then do the space optimization after that. I think this problem is also relatively easy to do space optimization. So yeah, because these are skills that you have to practice on the easier problems, because it only gets harder for that kind of stuff. But yeah, hopefully this logic makes sense. Yeah, that's all I have for this problem. Oh, did I submit it? I think once I actually did finish a problem, but then I forgot to submit it, and then I just almost missed a day because of it, like killed my streak or whatever. But yeah, so this looks good. Got accepted in case you didn't see, and that's all I have for this farm. Hit the like button, hit the subscribe button, join me on Discord. Hope y'all have a great rest of the month, and just like stay cool, stay good, stay healthy, and to good mental health. And I will see you later. Bye bye.